I want you to picture the most pristine environment on Earth. Like you are hiking high up in a remote mountain range.
Oh, yeah, the classic untouched wilderness.
Exactly. The air is painfully thin, and right beside your trail, there is this stream of water running directly off a melting glacier.
Just tumbling over those smooth river stones.
Right, and if you cup your hands to take a drink, you are almost certainly thinking, this is the purest, most untouched water on the planet.
I mean, everyone thinks that.
We all have that default image in our heads, of mountain water equating to absolute biological purity. Well, a 2020 review in the journal Applied Water Science completely shattered that illusion for me.
It is a beautiful image, but historically it might have been true, but unfortunately it is rapidly becoming a myth.
Yeah.
We are seeing a massive degradation of freshwater resources worldwide,
Hmm.
and it is reaching places we assumed were just untouchable.
And that is exactly what we are exploring in this deep dive. The review we're pulling from today specifically looks at water quality and dairy cattle health.
Right, with a very heavy emphasis on these fragile, high-altitude ecosystems.
Our mission today is to trace the actual journey of water, not just looking at whether we have enough of it in a drought, but really examining its physical and chemical quality.
Which is so often overlooked.
It really is.
Yeah.
We want to understand how a corrupted water supply at the top of the world fundamentally alters the entire food web, filtering through the biology of livestock and ultimately ending up right there in your glass of milk.
To map that journey accurately, we have to kind of reframe how we view water entirely.
How so?
Well, we typically view it as an environmental backdrop, but biologically, water is the ultimate most essential nutrient for all living organisms.
Right.
And right now, it is facing an unprecedented global crisis driven by rapid industrialization, the intensification of agriculture, tourism, and shifting climate patterns.
So it's everywhere.
Yeah, this isn't merely a localized drinking water issue for humans. It is a massive systemic disruption.
Okay, let's unpack this. Because if water is facing this kind of global crisis, my immediate thought goes to how that impacts agriculture at scale.
Right.
I mean, we obsess over what we feed livestock. You hear about dairy farmers optimizing feed down to the microgram.
Oh, absolutely. Getting the perfect mix of fermented silage and grains.
Yeah, but water seems to be treated as just, well, wet, like it's an afterthought. But if water is the primary input, how does poor quality actually disrupt the animal's biology?
It disrupts it profoundly because water isn't just a passive diluent. It is the active medium for literally every physiological process.
Wow.
While specialized food is indispensable for somatic growth, water supports the entire digestive process, the active transport of metabolites, and cellular communication.
So it's doing a lot of heavy lifting.
Exactly. It manages thermoregulation, which, is highly energetically demanding for a large mammal. It drives waste elimination. In pregnant animals, it provides the amniotic environment for developing fetuses.
And the sheer volume required is staggering, too. According to the review of all the landmass animals on Earth, dairy cows have the highest water requirements.
Yes, they do.
And the detail that stood out to me was that up to 80% of the water consumed by a dairy cow is utilized solely for milk synthesis.
Which makes perfect anatomical sense when you consider that bovine milk is about 87% water.
Right, right.
A single high-producing dairy cow can consume dozens of gallons of water a day. They need that massive fluid intake to maintain the osmotic pressure required to continuously draw nutrients from their bloodstream into the mammary glands.
I was trying to conceptualize this, and it made me think of a manufacturing plant.
Okay, I like that.
If the premium feed is the raw material, water acts as both the factory's conveyor belt and its coolant system.
That is a highly accurate way to look at it.
So if the coolant is full of sludge, the machines overheat, meaning thermoregulation fails. And if the conveyor belt stalls, nutrient transport stops entirely. The raw materials just sit there, useless.
Exactly. If the coolant system is corrupted, the factory's output just drops. Poor water quality directly alters the cow's feed intake.
So they just eat less.
Well, if the water is unpalatable and chemically imbalanced, they drink less. And if they drink less, rumen function slows down, they eat less, and the metabolic pathways become compromised.
So it's a chain reaction.
Completely. The quality of the water dictates the health of the animal and the nutritional profile of the milk.
Man, so if water is the factory coolant, we need to look at how that system gets polluted globally. The review breaks down water safety into 4 specific parameters: physical, chemical, microbiological, and trace elements.
Right. And researchers have to evaluate all of them together to get a real picture of water safety.
But instead of just listing them out, let's look at how they actually work. Take total dissolved solids, or TDS, which is a physical parameter.
Yes.
My initial assumption was that you'd want water with the lowest possible TDS. Like, you'd want pure H2O, right?
Logically, you would think that closer to pure H2O is better, but biology is incredibly sensitive to osmotic balance.
Right. Okay.
The data actually shows a highly counterintuitive mechanism. If the total dissolved solids are too low, cattle will actively decrease their water intake.
Wait, really? What? This seems so backward. Why would an animal reject pure water?
Because of how their cells manage hydration. Pure water lacks the essential electrolytes, like sodium, potassium, and chloride, that actually facilitate cellular absorption.
Oh,
If a massive animal drinks dozens of gallons of zero TDS water, they risk diluting their blood plasma to a dangerous degree.
oh, wow.
Yeah, potentially causing hyponatremia. So they instinctively pull back their intake to protect their internal mineral balance. So the water actually requires a specific baseline of dissolved minerals to be biologically useful.
That is fascinating. But the pendulum swings the other way, too. If the TDS is too high or made of the wrong compounds, you hit toxicity.
Exactly.
And that brings us to where agriculture sources this massive amount of water. About a third of the global population and a huge percentage of agriculture relies entirely on groundwater.
Yes, and in India alone, 70% of total water resources are severely polluted.
70%. That's terrifying. I think the common assumption is that aquifers are perfectly filtered. Like, it's deep underground, separated from human activity by hundreds of feet of rock and soil.
That assumption is precisely why groundwater contamination is such an insidious problem.
Because we can't see it.
It is completely invisible. Groundwater is currently being heavily contaminated by industrial discharge, sewage infiltration, and intense agricultural runoff.
Like fertilizers.
Specifically nitrogen fertilizers and synthetic pesticides. And the critical mechanism to understand here is that groundwater lacks the natural remediation processes found on the surface.
Because it's trapped in the dark.
Exactly. Surface rivers have flow dynamics, aeration, and exposure to ultraviolet light from the sun, which naturally degrades certain chemicals and bacteria.
Oh, right.
Groundwater is largely static, cold, and devoid of sunlight or high oxygen levels. When heavy metals or synthetic chemicals infiltrate an aquifer, there's almost no biological breakdown.
It just sits there.
It just acts as a chemical sink. Once it is contaminated, it can persist in a toxic state for decades, silently being pumped up into agricultural troughs.
Okay, so aquifers in populated agricultural plains are vulnerable. I understand that. But this brings us back to the core focus of the review, the mountains.
Right. This raises an important question. What happens when we look at the parts of the globe we assume are immune to this pollution?
The high-altitude regions. Mountainous ecosystems cover 1/5 of the Earth's surface and provide fresh water to over 1 billion people.
A massive portion of humanity.
And we define these vulnerable zones in the review as anything starting from 2,400 meters above mean sea level.
And these are regions that depend entirely on glaciers, snowmelt, and mountain springs. Historically, they were shielded by their extreme isolation and harsh climates.
But not anymore.
No. Global warming is drastically altering precipitation and accelerating glacier retreat.
It's not just the climate, though. It's the physical human footprint. The review highlights a case study from Ladakh in India.
Yes, a high-altitude cold desert.
Since 1996, the tourist load there has increased a staggering 100 times over.
Which is just explosive growth.
You have hundreds of thousands of people suddenly flocking to an ecosystem that biologically and infrastructurally cannot process that volume of human waste.
It creates a localized environmental collapse.
Right.
You have less water available due to unpredictable snowmelt, and the water that is available is subjected to raw sewage infiltration from unregulated tourism camps.
Disgusting.
But the localized pollution is only half the story. The more alarming threat comes from POPs.
Persistent organic pollutants. These are synthetic industrial chemicals like DDT and polychlorinated biphenyls or PCBs. But I have to push back here.
Okay.
I completely get how localized tourist trash ruins a mountain stream. But how does an industrial chemical from a manufacturing plant at sea level end up locked inside a glacier at 15,000 feet? That essentially defies gravity.
It does sound impossible until you look at global atmospheric dynamics. It's a phenomenon known as the grasshopper effect or global distillation.
The grasshopper effect.
Yeah. These synthetic chemicals evaporate in warmer climates down at sea level. They become airborne and are caught in global wind currents. They travel thousands of miles through the atmosphere until they hit the cold air of high-altitude mountain ranges.
So the temperature drop physically forces them out of the sky?
Precisely. The cold air causes them to condense and precipitate out. They literally fall with the snow and become lodged deep within the ice layers of the glaciers.
Wow.
For decades, they have been somewhat trapped there. But now, as global temperatures rise and those glaciers undergo rapid, unprecedented melting, those concentrated industrial chemicals are being continuously released directly into the pristine headwaters.
That is deeply unsettling. So here's where it gets really interesting. Because of this global distillation and local tourism, the review notes that major Himalayan rivers like the Ganga and Alaknanda rivers fed by the highest peaks on Earth are now contaminated with E. coli and synthetic chemicals before they even reach the plains.
Yes, it's tragic.
The myth of pure mountain water isn't just broken, it's practically inverted. The mountains are acting as a storage vault for global pollution.
And that leads us to the most critical phase of our deep dive. We now know exactly how the water is corrupted, even at high altitudes. The next step is looking at the cellular impact when a dairy cow consumes that corrupted runoff.
Right. How do these specific contaminants interact with bovine anatomy?
Well, let's start with trace elements, because they have a dual nature.
Like essential minerals versus toxic ones?
Exactly. Some are essential cofactors for enzymes like iron, copper, zinc, selenium. But then you have toxic heavy metals, lead, arsenic, cadmium, entering the water through mining, industry, and weathering.
And the review outlines a really wild behavioral quirk with this. It notes that lead poisoning is incredibly common in young calves.
It really is.
Not just from ambient water, but because calves are naturally curious and will, lick machinery grease, drink discarded crankcase oil, or chew on old batteries left around the pasture.
It's a significant behavioral risk factor. And what makes heavy metal ingestion so devastating for cattle isn't just the toxicity of the metal, it's the specific anatomy of their digestive tract.
Right, because when a cow ingests lead, arsenic, or cadmium, it doesn't just pass through them smoothly.
No, it gets trapped.
In the reticulum.
Yes, the reticulum is the second chamber of a cow's stomach, and its internal lining has a highly textured, honeycomb-like structure.
Oh, like a net.
Its biological purpose is to catch dense, foreign objects so they don't puncture the rest of the digestive tract. But this means that heavy metals settle deep within that honeycomb structure. They don't pass.
They just sit there.
Instead, they sit in the highly acidic environment of the stomach and continuously leach toxic ions directly into the animal's bloodstream over months or years.
And once it's in the bloodstream, how does it damage the animal?
Heavy metals are notorious for cellular mimicry. Lead, for example, mimics calcium.
Oh, that sounds bad.
It is. The cow's body thinks it's calcium and incorporates it into bone tissue, the nervous system, and enzymatic pathways. But lead doesn't function like calcium, so it paralyzes cellular processes, leading to severe neurological damage, immune suppression, and a catastrophic drop in milk synthesis.
And right alongside those heavy metals, you have the microbiological threats we touched on earlier, like the E. coli coming off the Himalayan runoff.
The microbiological threat operates on a different but equally destructive mechanism. Pathogenic bacteria like E. coli and total coliforms indicate direct fecal contamination.
Right.
When consumed, these bacteria attach to the intestinal lining and release toxins that damage the villi, which are the tiny structures responsible for absorbing nutrients.
So going back to the factory metaphor, the conveyor belt is physically destroyed. Even if you feed the cow perfectly, they literally cannot absorb the nutrients.
Exactly. It causes severe gastrointestinal inflammation, massive fluid loss through diarrhea, and completely halts their metabolic productivity. And the terrifying part of bacterial contamination is its amplification potential. The review highlights that just one single liter of heavily contaminated water can easily pollute 8 liters of clean water in a shared trough.
Just 1 liter.
Yeah. The contamination multiplies exponentially.
So this isn't an acute toxicity issue where the cow just gets a stomach ache, clears the pathogen, and goes back to normal. We are talking about chronic cellular retention of heavy metals and severe gastrointestinal destruction.
Unfortunately, yes.
But this brings us to the ultimate destination of this journey and really the crux of why this matters to you, the listener.
If we connect this to the bigger picture, it is the transition from environmental hazard to human health hazard.
Right. We've traced the atmospheric pollutants falling on the mountain snow, melting into the river, gathering heavy metals, and being ingested by the dairy cow. How does that leap from the cow to the consumer?
Through the biological mechanism of bioaccumulation. When a cow ingests these persistent organic pollutants, those PCBs and industrial chemicals we discussed, they face a unique problem.
Mm.
Many of these POPs are lipophilic, meaning they are fat-soluble.
Oh, okay.
Cow's body cannot easily break them down or excrete them in urine.
Because they bind specifically to lipid molecules.
Exactly. So they bioaccumulate, they build up in the animal's adipose tissue, their body fat. And in dairy cattle, there is a massive daily mobilization of fat, specifically to produce milk.
Oh, no.
As a result, these toxic fat-soluble molecules are secreted directly into the milk fat.
And the heavy metals.
Similar concept, metals like cadmium and arsenic accumulate in the organs. But heavy metals like lead, which again mimics calcium, are secreted into the milk right alongside the actual calcium that consumers seek out for bone health.
That is a staggering realization. So what does this all mean? Poor water quality is not simply an agricultural overhead cost.
Not at all.
It isn't just about a thirsty cow or a farmer facing reduced yields. It means that these persistent molecules, whether that's arsenic from local mining or atmospheric PCBs from a factory on another continent, are actively transferring up the food chain.
Directly to us.
The cow is effectively acting as a biological concentrator, taking trace amounts of environmental pollution and bottling it directly into a public health hazard.
That is the ultimate takeaway from the scientific community here. Reactive, symptom-based measures are completely inadequate. The only way to protect both the agricultural supply chain and human health is through continuous, rigorous evaluation of water quality at the source.
Yeah.
That requires evaluating the physical, chemical, and biological parameters comprehensively. As climate change continues to alter our hydrology and force reliance on increasingly vulnerable aquifers, monitoring the input is the only way we can trust the output.
We've gone on quite an intense journey today. We started at the top of the world with a high-altitude snowflake that we assumed was biologically pure.
And found out it wasn't.
Yeah. We watched it melt, pick up locally distilled industrial pollutants, flow down a mountain river, mingle with unregulated tourist waste and agricultural runoff, be consumed by a dairy cow, trap itself in the animal's anatomy, and ultimately secrete into the human food chain. It really exposes how delicate and interconnected this entire system is.
It certainly does. And while we focused heavily on the local consumer of that milk, I want to leave you with an even broader implication to consider.
What's that?
Think about the globalized nature of dairy commodities. A massive amount of the milk produced in these regions isn't just consumed locally as fluid milk. It is dehydrated, turned into milk powder, and shipped worldwide as a base ingredient for countless products.
Including infant formula.
Exactly, including infant formula. Which means that because of the global distillation of POPs and the lack of comprehensive water monitoring, a pollutant that evaporated from a factory in one hemisphere can fall on a mountain in another, bioaccumulate in the local dairy herd, be processed into formula, and end up feeding an infant on a completely different continent.
That is chilling.
Local mountain pollution is no longer local. It can almost instantly become the dietary baseline for the most vulnerable populations globally. Think about the water locked inside the ice or snow on the highest mountains right now. Because of global warming and global pollution, a snowflake that fell decades ago might be carrying industrial chemicals from a factory thousands of miles away.
Wow.
As that ice melts tomorrow, it becomes the grass a cow eats and the milk you drink next week. When you take a sip of milk, you aren't just tasting local agriculture. You might be tasting the atmospheric history of the entire planet, something to think about the next time you pour a glass.
That reframes everything. A localized water issue is essentially a globally exported health metric. That is incredibly provocative and definitely something that will stick with me. A huge thank you to you, our listener, for joining us on this deep dive. Keep questioning the inputs of your world, look past the pristine surfaces, and always remember to interrogate the invisible systems that connect us all. Until next time.